In this video, we're talking about multiplication and division of like terms. And before we get to that, I want to review briefly what we learned when we talked about addition and subtraction of like terms. Remember when we were dealing with addition and subtraction, we said that our variable had to be the same and the exponent had to be the same. So for example, if we wanted to add together x squared and 3x squared, what we need to confirm is that both the variable and the exponent are the same. So in this case, the variable is the same in both terms, it's x. The exponent is 2 in both terms, which means that x squared and 3x squared are like terms. The fact that we have a 3x squared here as the coefficient just tells us we have 3 of them, versus in this first term here, we have 1 of them. This 1 is just implied, so we don't write it. So when we have 1 of them and we add to that 3 of them, 1 plus 3, we get 4. So this is going to be equal to 4x squared. We keep the like term of x squared together. So that's addition of like terms. Here, if we try to add together an x squared and an x cubed, our x's are the same, the variable is the same, but the exponent is a 2 versus a 3. And because the exponents are different, these are not like terms, and we can't simplify this at all. We can't add these terms together, so these are not like terms. Like terms get a little different though when it comes to multiplication and division. When we deal with multiplication and division, all we care about is that the base is the same, the variable or the letter, not that the exponent is the same. So for example, if we have a squared times b cubed, because these are sitting right next to each other, we know it's multiplication. All we need to look at is whether or not the bases are the same. So this one has a base a, the variable a, and this one has a base b. Because they're not the same, because a and b are not the same, a squared and b cubed are not like terms, we can't simplify this at all, so we can't simplify that. If, on the other hand, we have the same bases, so here we have base a and base a, they're raised to different exponents. We have a squared and a cubed, but because we're doing multiplication, all that matters is the base. And so these are in fact like terms, and we can multiply them together to simplify this expression. The way that we do that is just a rule of exponents. We get a base a, but then we add our exponents together. So 2 plus 3 becomes our new exponent, and this simplifies to a to the 5th power. And this should make sense to us because if we multiply these together, we see a squared is a times a, and then we know a cubed is a times a times a, and of course when we multiply all these together, we get a to the 5th. Same thing goes for like terms when we're doing division. Remember when we had addition and subtraction, the base, the variable, the letter, and the exponent both had to be the same. For multiplication and division, only the base has to be the same. The exponents can be different. Here though, we have different bases. We have base A and we have base B, so there's nothing we can do here to simplify this expression. On the other hand, in this example, we have a squared divided by a cubed. We can clearly see that we have like bases. Both of these terms have base a. So because they're like bases and we're doing division, we can go ahead and combine these two terms even though the exponents are not the same. So in this case, when you have division, the rule is always keep the base the same, then raise this to the exponent from the numerator, 2 in this case, minus the exponent from the denominator, which in this case is 3. This simplifies to a to the negative 1 because 2 minus 3 is negative 1. And now we need to realize that a to the negative 1 is the same thing as 1 times a to the negative 1, which is the same thing as 1 times a to the negative 1 divided by 1. The reason we put these understood ones here is because we want to make this exponent positive, and in order to make the exponent positive, we need to take this a to the negative 1 value and move it to the denominator. So when we move it to the denominator, we're going to be left with this understood 1 in the numerator. In the denominator, we're going to have 1 times, moving a to the negative 1 to the denominator makes the exponent positive, so this becomes a to the positive 1 in the denominator. And remember that that's always the case. When you have a negative exponent in the numerator, you can make it positive by moving it to the denominator. If you had a to the negative 1 in the denominator, you could make the exponent positive by moving it to the numerator. So just by switching its place, you make that exponent positive. And now this, of course, we can simplify to 1 over a, because this understood 1 can be dropped and this understood 1 can be dropped. So our final answer is 1 over a. Let's look at another example where we have x squared y squared divided by x to the 5th y to the 5th. Well, we're going to deal with our x's together. We have this like base of x. In the numerator we have x squared, in the denominator we have x to the 5th, and then we're going to deal separately with our y terms where we have y squared and y to the 5th. So again, dealing with our x's here, we'll get x to the 2 minus 5 when we take the numerator exponent minus the denominator exponent, and then that's going to be multiplied by y to the 2 minus 5. And that's the case because you can think of this here as essentially x squared over x to the 5th times y squared over y to the fifth. That's the same thing. So that's why we can deal with the x's separately and then multiply by whatever we get when we simplify this y squared over y to the fifth. So we end up with this here, and of course that's going to be x to the negative 3 times y to the negative 3. And now we have negative exponents. Remember, we have this implied 1 in the denominator. So we can move these two values to the denominator, and we end up with 1 over x cubed y cubed for our final answer. Now keep in mind that this is the formula you should use, where you subtract the denominator exponent from the numerator exponent. You do numerator minus denominator. That formula will work every time, and it's the safest way to make sure you get the right answer. But you can always just sort of logically double check yourself by remembering that the terms that you end up with in your final answer are always going to be wherever you had the largest exponents in your original problem. So for example, if I look at the last example here, where I had an exponent of 2 in the numerator and an exponent of 3 in the denominator, because the 3 was larger, I knew that my a term was going to end up in the denominator, and it did, because the larger exponent is in the denominator. Same thing here for my x terms. I have the larger exponent in the denominator, so x ends up in the denominator. And for y, I have the larger exponent in the denominator, so y is going to end up in the denominator. In other words, if, for example, I was just going to deal with this x squared over x to the fifth, I could just take my exponents. I have 5 and 2. The larger one is 5, so I'll just say 5 minus 2. That's going to be equal to 3. So I know the result is going to be x cubed, and now I just need to know where it is. Well, I know it's going to be in the denominator because 5 is larger than 2, so I can just take x cubed and put it in the denominator like I did here. So either way is going to work. You can just consistently take the numerator exponent minus the denominator exponent and you'll get the right answer. Or you can look for the larger exponent, subtract the smaller exponent to get your answer for the exponent, and then put the term wherever the larger exponent exists.